Good afternoon, my name is Brent. I'm here with my teammates Dominic and Alejandro. Our faculty advisor is Dr. Bellotti. We're going to discuss to you our solar-powered attic fan. Our governing motivation here basically was a result of temperatures in attic reaching about 140 degrees in the summertime in South Florida. Infiltrations or leakage into the household can put an extra strain on the AC. Also, unwanted humidity can present a problem with mold, potential mold. This makes it increasingly difficult to store valued items, as well as contributes to energy loss. Part of the solutions people implement these days are turbines, fans. They can be visually unappealing, provide not really a whole lot of ventilation at the end of the day, and some of them do consume power. So it's kind of, they help you save money, but then they spend money at the same time. Most of these items have been on the market for some time now. The problem with them is that they don't implement any type of rechargeable battery. So if there's no sun, there's no fan spinning, there's no ventilating on your attic. They're basically underpowered in the sense that the average solar-powered attic fan on the market today is about 400 to 500, maybe 600 cubic feet per minute as far as air ventilation. That is ideal for some attics, but in other states where you have a larger attic, it's not really helping you a whole lot. As well, there's one solar panel, so the geographic orientation on the roof kind of forces you to put it where you're going to get the maximum optimal sun exposure. It may be on a portion of your house that's unappealing where you don't want anyone to see it, so it's hard to hide these things from your neighbors. General design consists of a photovoltaic cell, which is going to charge a battery, which you see on the bottom left here. Battery then governs a motor-driven fan, and then a series of intermediate electrical components will govern the behavior of this. Major components we're going to use, we're using 4 SunForce trickle charger solar panels, which they're called. We run them in parallel at about 15 volts. They basically produce about a third of an amp. And we have diodes that prevent reverse discharge from the battery, from the solar cell to go back into the battery. So that's not, it's going to be basically a one-way current flow. We have a pulse width modulator in a nutshell. This is basically to govern the speed of the fan depending on the needs of your attic. You can go to 100 CFMs up to 2,000 CFMs depending on what you need and how quickly you want to do it. So charge controller, these are very common with any type of solar system. It basically governs the battery, makes sure there's no accidental discharge, allocates voltage and current, and basically it's kind of a necessity anytime you're dealing with PV cells. Our deep cycle battery, which is different about this, it's unlike car batteries. This can be completely discharged and recharged many cycles, many times per day, week, year. So it's ideal for any type of charging system that you're getting alternative energy from. This is basically the backbone of our project. It's basically governed for a 350 cubic inch Chevy engine, so if it's good enough for that, it's good enough to move air out of an attic, we thought. It's very lightweight. It's basically able to operate in very high temperature environments, and it really requires a low amount of current to run. As I mentioned earlier, it's about 2,000 CFM rating. Part of our automatic control system here is the implementation of 2 timers we have. Basically, they will work alternating with each other. One timer will go, for example, for about 60 seconds where it rotates the fan, expelling air. We then have an intermediate period where the timer lies dormant. Then another timer will kick in with a reverse polarity. The beauty of DC current, we can spin the fan in the opposite direction and actually intake air, fresh air from the outside, depending on what your geographic weather conditions are and your needs for ventilating your attic. This is basically the best aspect of our design. It's what separates it from all the ones on the market. As far as we know, nothing on the market offers these dual natures here as far as intake and outtake of air under one design. So that's pretty much our pride and joy of this design here. This is basically the electrical system minus 3 other panels. As you can see, the PV panel charges the battery, runs the fan to the charge controller. This is our housing, final product, as you can see in front of you. Basically everything was made from a sheet of aluminum that we cut and bent ourselves. This is our control system. You see the 2 timers, the charge controller, and the pulse width modulator is buried in the back there in conjunction with the deep cycle battery. I'm going to let Alejandro come in, or sorry, Dominic come in and discuss our timeline and things of the sort.
All right, so as you can see, basically we started in senior 1, we got up to our research process, we did the fundamental design. This semester, second semester, we developed what you see in front of you. We began assembly about a month ago, and then testing was kind of tricky, but we got some initial testing done.
Regarding the literature survey, attic fans, solar powered attics, and photovoltaic set. Next slide, please. We have the attic fan using also in warm and cold climates. In summer mode, the temperature on the attic can reach over the 160 Fahrenheit. Moisture and cold can lead the mildew growing in attics as well on winter season. As you see in this slide, you have an example of in winter mode how the moisture can create into the attics. So we have a comparison the before and after. We connect the attic fan. The idea is to keep the outside temperature at the same inside temperature to prevent the snow melt on the roof. The heat on the attic is going to refreeze everything during the night. So in summer season, the attics, as you see, the temperature can reach over the 170 degrees. When you have the unvent part of the house, and then in contrast we have the vented side of the house, we can reach temperature of 150 degrees. So the solar attic fans are available for all the customers in the most common retail store as Home Depot, Lowe's. But the product are no efficiency, they are limited to solar photovoltaic cells, so our product has a battery incorporated. So, and also we try to do some aesthetically better than we have on the market. This is one of the diagram of how the photovoltaic works. They take solar radiation from the sun and then take this electrical current to the controller charger, and then they're going to deliver to the battery in DC power or to an inverter to convert the AC power. So the environmental impact of this project, most of the components cause no threat to the environmental. The battery is completely rechargeable, runs on direct current, and because of this, it's ideal to be installing in any location. So the next slide, please. This one, the photovoltaic cell, as all know, they are generate a large amount of electricity without producing any pollution to the ambient. Photovoltaic cell also can have a working life about 30 years. So the company, the manufacturing company that built this kind of product has a lot of laws against they has a lot of chemical control to the environment. So next slide, please. The electronic component was not threat also to the environmental. They no impact to the inventing ambient or manufacturing process, and optimize the equipment used to extend the operation hours. The rechargeable battery is another big. There has a 96% of the components that are rechargeable. The lead-acid battery contains about 60 and 80% of plastic that we can is recyclable also. About the fan, as you see, we can call winding anytime. 90% of the part are built in the plastic. So next slide, please. So for all this, we have all the standard that we follow this when we try to design this experiment. So one of the standards that we use in building the aluminum body is the ASM, American Society of Metal. So I'm going to let Dominic to explain the environmental concern.
All right, especially being that we live in South Florida, every couple months, especially during the summer periods, we get we're affected by tropical storms and hurricanes. As such, we needed to take this into consideration when we were designing. Tropical storms, according to the Saffir-Simpson scale, we have different categories for when you storm up to a category 5. That wasn't included here because it wasn't taken into consideration for the design. It was the wind loading, which would result from category 5. Winds would be too great. And as I said about wind loadings, we use this formula to determine the wind loading which would occur, assuming the winds are hitting the prototype perpendicular. The CD there stands for the coefficient of drag. In order to accurately determine that we need a wind tunnel and etc., that was beyond what we needed to do for this project. So based on research, it ranges from 1.2 to 1.65. I chose 1.65 in order to account for all conditions. And this is a design that we did in SolidWorks, as you can see here in the meshing. If you notice at the back, the rear, one of the flanges has been eliminated. It wouldn't play much of a role in the analysis, and in addition to that, SolidWorks, I think that's part of the reason SolidWorks wasn't capable of doing the analysis with that flange in the model. So this figure shows the results of tropical storm conditions. As you can see here, the safety factor is about 1.2, and this scale shows you the stresses incorporated throughout the figure. As you expect, a lot of the flanges you have the greatest stresses concentrated. And this is for category 1 loading. As you can see, the safety factor is less than 1. Stresses within the flanges exceed 49 megapascals. And based on the figures before, as you can see, I never went beyond the category 1 loading because, as I said, it's below a safety factor of 1, so naturally it would only get lower. So in order to, naturally, as such, the housing would need to be fastened, and our recommendation is to use number 8x2 screw, self-tapping, galvanized, because it's going to be exposed to the elements. This was chosen based on ASTM standards. And just for a reference, 600, if we were to go ahead and make this into a product that's available to the consumer, 650 screws cost $34. And one thing I'd also like to mention, as you saw in the previous figure, the fasteners aren't the actual where failure would occur because the stresses are concentrated in within the flanges. The housing would more like the flanges, based on the studies we did, the flanges would remain attached to the housing. The body of the prototype is where failure would occur. And is that what I just explained? And this is just a flow model, and as you can see here, maximum velocity, as we expected with the dome, is around the lips. It's about 4.4 meters per second. We chose that shape because it would produce the least amount of backflow and back pressure. And as I just stated, because of the higher velocities within these areas, you expect the greatest pressures to be concentrated in those areas as well. And this is just the video to demonstrate the flow patterns that we'd expect.
So the fun part was the testing of this apparatus to see what our hard work went to. We basically, due to availability, had to isolate our testing to one attic. It's hard to get people to donate their attics to you, especially when you have
If you go from, I'm afraid to go up there.
The problem with it is that if you do have a makeshift turbine, like the ones I demonstrated earlier, just a convection turbine, you have to take that off to allow yourself access to the hole through the roof. You then have to test, bring your apparatus up on the roof, let it there, have somebody in the attic to govern it from underneath. And then in the case of rain, if it does happen to rain, you have to leave this on the roof, or you have about 10 minutes or so in the rain to get the turbine back on. In some cases, they require ducking tape and other fastening. So it's not something you want to do when it's cloudy outside for obvious reasons. So we weren't able to obtain as many testing trials as we wanted. However, we were very pleased with the results for the trials that we did do. This is basically the remote you see on the bottom. That's a temperature gauge. It stays in the attic. The device that you see on the right is our temperature display, and that can be within 20 feet of the remote without causing any sort of errors or fluctuations. So that was our bread and butter as far as the results were. We basically would test the attic before, run the unit for time intervals, which I'll show you in just a minute, and see what the temperature was after and see what our results were. What you can see is that we wanted a little higher temperatures to work with, and I'm going to address that in a little bit. Being the time of year that it is, we don't have the nice summer temperature of the 130 to 160 degree attics that I was talking about earlier. I don't know if that's a good or bad thing, but we made the best of it. So nevertheless, the hottest day we were able to find was 85 degrees within the last 2.5 weeks. In between that, we had cold fronts and rain, making it harder, so we had to basically work with what we got. At the end of the day, you can see our attic temperatures were based on preliminary temperature with no ventilation at all, as is. We then had a fan that's enclosed inside the apparatus here that we didn't have it on its maximum speed. We wanted to see what it did in its lightweight mode. So we ran it with about 1.8 amps at 600 CFMs for 90 seconds. Let the timer stop, rested for about 60 to 90 seconds. Then the reverse polarity kicked in and actually took in air from the outside into the attic. And that was at a smaller CFM because of the orientation of the blades and whatnot. We only get about 200 CFMs, but we're not trying to bring a whole lot of air into the attic. And that basically resulted in a temperature change of what you see here on the right as almost 14, 17, and 16 degrees respectively from start to finish. But this was all over about 4 or 5 minutes in time. So we can imagine where we would be if we had this totally self-sustaining, running automatically. It doesn't need any human interaction. It has potential to run 17 cycles a day, off and on, clockwise, counterclockwise, intake, outtake. And you can obviously see what it can do on hotter days as well. We can notice the trend that it would probably lower the attic temperature to 20, 30, maybe 40 degrees. And hopefully we'll find out sooner or later what its potential is. Something I said during our last presentation back in May that kind of came back to hit me, just run it by you real fast. If we have volume, which I don't think we do. Basically what I said here is somebody asked if we were going to build this and when we were going to test it, and according to our timeline, I told them, yes, we were going to build it, yes, we're going to test it, and I jokingly said in December when it's cold. Obviously, we had some design problems. We weren't able to start testing it until late November. Then we had the rain and we had the cold front, so we actually did our last day of testing yesterday in December. It wasn't quite cold, but it was the cold that stopped me from getting 25, 30 trials rather than 3. So you got to be careful what you say sometimes in jokingly. So. Basically, in conclusion, there's a lot of systematic ways we can govern as far as how much there's going to save you in electricity by keeping your attic cooler, how much strain it's going to take off on your AC. There's really no cut and dry. Some controversy says that the attic fans will take air out of cold air and bring them up into your roof and leak them out and ruin it for everyone. That's only if you have really poor infiltrations and leaks and insulation and things of the sort. So we basically just went with a general one, very modest, based on the low CFM movement that we had. Like I said, with 17 cycles a day, day and night, with or without sun. The battery can still sustain itself even if you have cloudy days. It's got 35 amp hours, so it doesn't need a lot of sun to hold and sustain itself for a good 5 to 7 days. And basically it came out to about 4.31 kilowatts per day in savings for the most part, and we basically equated that to, it didn't make it to the PowerPoint on such short notice, but it basically coming in about to $250 to $300 per year. Like I said, those are based under modest conditions at about 600 CFMs. The potential here is for 2,000. So depending on the time intervals we tweak and find out what's optimal, we hope that that number could even get higher. But nevertheless, it pays for itself pretty quickly. Yeah, and in a nutshell, I guess we'll give you a quick demonstration as far as these are the two timers that are going to oscillate clockwise, counterclockwise, or counterclockwise, clockwise. And I'm just going to do it manually. Initially, I wanted to have the timers oscillate while I was giving the presentation, but we realized that was going to be too loud and distracting. Watch your hands. I have it here up to full speed. This is as loud as it gets at 2,000 CFMs. So if it's up in your attic and on your roof, you're not going to hear this. The noise from your air conditioner is going to by far outweigh this noise. So we're happy with that in the sense that it's pleasing to people in that sense. It has a slow discharge rate from the capacitor, so we realized the hard way that you can't have these connect real quickly because capacitors hold energy, and you know what happens when we cross polarities. So with that, that'll conclude our presentation today.
Did it cool off by 5? All right.
Okay, so I'll start off. First question I want to ask is near to my heart is Hurricane Andrew. This particular structure, as I'm looking at here, you did not test in your testing for hurricanes, because you basically tested the substructure, you didn't test the whole assembly. How do you think this whole assembly would handle
Yeah, I mentioned that
Hurricane
in the
Andrew?
presentation, which I should. We recommend, as I said, the failure would occur within the housing because of the high coefficient of drag, so the
Do you
flanges.
think that's the case? I mean, I would probably think I'd pop that top right off the bat.
Well, that's what you took earlier, right?
What-
You will remove the,
No, that top would
you
come
will
flying.
remove these cards.
Yeah, these-
Oh, you're gonna have to take that off before
Yeah.
I see
Yeah,
it.
that's what I was gonna say, the flanges.
Or remove the whole thing.
Yes,
Give us.
because of, as I said, the safety factor for a tropical storm is 1.2. Anything greater than that, we recommend taking it off and sealing
Seal it off.
the hole because of the high coefficient of drag. That's one of the disadvantages of this shape.
Okay, your question. In your design requirements, you said you designed a tetrahedral shaped housing for solar cell that would allow maximum solar absorption regardless of position. What data do you have to defend that statement?
Due to cost limitations, that was our initial guideline. We wanted to have like the image that I showed you earlier. It was a complete nice pyramid shape. We realized what the cost was going to be and opted against it. We didn't have the funding for it, so by tetrahedral, meaning we have geometrically oriented four sides. It's not quite the pyramid shape from a topological standpoint, but that's the reason for the change. We didn't have the funding to create it that way, so we had to do the best we could with the 4 panels that we had.
Okay. Okay, and then the last question I'm going to ask is, you made the statement that you're going to use galvanized screws to put this into your roof.
Yeah.
What is that structure? It's aluminum?
Yeah,
Would that be a problem? Galvanized into aluminum?
from my knowledge, that's it.
Okay.
You can correct me.
Yeah, it's a problem.
I know.
Okay, thank you.
My question relates to structural. I mean, you're gonna have to get those long screw into something. What are you gonna get those screws into? Just the sheathing or into the trusses?
The sheeting.
And do you think that a modest wind load on that wouldn't blow it off if it's just anchored to the sheeting?
Yeah, that's why I said earlier, I think the safety factor on the tropical storm condition is 1.2, so honestly, if this were to go to a general consumer, I'd say remove it for tropical storm conditions.
No, I'm saying a modest wind.
Oh, what
I
do you
mean, like 30, 40 mile an hour wind.
Yeah, that's tropical
it's
storm
just-
conditions, that's because it's based from like, I want to say 28 up to like 42 miles per hour for tropical storm conditions. I just, in the calculations, I used as I did with the coefficient of drag, I used the upper limit, so 30, 40 miles per hour would be within that tropical storm conditions.
If I may add the flashing area here, our design we decided to end where the civil engineering aspect takes over. These would ideally be a lot longer anytime you're dealing with flashing under shingles or tiles. In systems of this sort, you'll see this area come out way underneath, so it's got all that support from all the areas. We chose to neglect that for time constraints. We wanted to focus more on the HVAC, mechanical, electrical principles of the apparatus. So basically, as far as the structure, the best advice we had is like a satellite dish. If the storm's going to be really bad, you might have to take it off your roof.
I don't understand how it works. Sorry.
No, that's all right.
You have your fan here, and then that casing sits on top of the roof?
The fan is about here.
Okay.
This goes on top of the roof. The attic will have its ventilation hole, and most houses have, say, about here. The apparatus fits right over it, and therefore it forms a tight seal where air can come out and come in. There is ventilation through these. You can't see them. You're welcome to come up afterward. We have a lot of space under here.
Oh, that's what I was wondering. Where is the air going to go?
Right, as far as the panels here, we try to get some that, we hope that these can be adjustable. They don't need to be almost perpendicular to this design all the time in order to get there. The whole point of having the 4 is that we can have them at an angle, and no matter where the sun is, it's going to get exposure to some degree. We had them up basically because these were the best way to do this hardware on the time and budget that we had. Ideally, we would want to have them lower, and we actually calculated that the area of this, say, rectangle, if you will, basically where the runoff of this hemisphere runs, the area of this runoff area is actually 1% greater than the area of the rectangle. So as far as back pressure and airflow, it's going to have no problem
So
going
the
out.
air will come up through that tube from the fan.
Correct. And
and
you're welcome to come
disperse
afterwards.
out through the salad bowl.
Right, through here.
Okay.
So basically,
Looks like a salad bowl.
when you measure the distance of the overhang, here,
It is a
here,
salad bowl.
it was about $300 to have somebody custom weld something for
course.
us. We bought this for 22.
Okay.
So
I like
basically,
that.
when you have the rectangle here, this leftover area
I see what you're saying.
basically
Thank you for
equals the
showing
area
that.
here.
So
So
there's plenty of
plenty of
place
room for the air to
go.
come in and come out,
I
sure.
see what you're saying. Oh, that's clever.
Well, you should get in the solid mold manufacturing business.
I didn't make it.
Yes, just a couple quick questions come. So I kind of made a sneer, but I had the same question, right? It's a little bit hard to tell how it works, so don't feel bad, Stephanie.
Okay, thank you. I feel better
So a
now.
couple other questions would just be, well, first the comment is, I'm happy with what you guys did because understandably, right, you're not gonna try to do, make a production product just going through senior design, but you guys you did really good engineering here by coming up with solid solutions at a cheap cost. So first things first, that's really interesting. I think it's really
Interesting
commendable.
project.
The other thing is, I understand why you want it all in one, but why not separate some of these components, especially like the solar panels, right? I mean, there's really not a whole reason why those solar panels have to be located right on that structure. And in fact, it's way worse to have them there, right? Because then you got to go up and take them off and all sorts of things like that. Maybe it's just easier to put the solar panels on a little platform right next to this thing and remove that, right? So just some questions like that. If going now in the future, from what you've learned from this initial thing, is there anything where you would redesign? I mean, to me, another thing would be make it a permanent structure, cut a hole in your roof, put all this stuff below and just have the vents come out, right? There's a whole bunch of different things you could do to kind of mitigate a lot of the hurricane issues and all sorts of other things like that. So is there anything you guys would recommend?
That crossed our mind back in senior one way back.
Okay.
When the gentleman brought up earlier about the tetrahedral shape, that was our biggest. It's easy, you can set it there. We were going with the set it and forget it approach, meaning automatic control system. You don't have to mess with these settings. Once you set it, it's self-sustaining, it charges itself, it has ample reserve. And in conjunction to that, when most people that we know that want to set up, and especially in the HVAC field, when they think of I got to put solar panels on my roof, it's a big deal. And I think that's why a lot of people, I don't have market research to back this up, but just from HVAC professionals that we've gotten feedback from, that's the hindrance as far as people wanting to go green, is setting up these panels. We thought that if you're going to put something on your fan, which people are going to do anyway, and most roofs come with the structure cut open, that's it. You fasten this and everything else is attached and you don't have to touch it. I do agree that it would probably be more beneficial or optimal, but what I brought up in the beginning of the slides was that because of the orientation of roofs, wherever your sun is, basically if your house, say, faces north, you know, the sun's not coming up there, but if it's in any other direction, you may see these. Depending on the orientation of the roof, you put your panel here where it needs to be, but then when you pull up in your driveway, there's the panel, I don't want to look at that. So that was our fundamental motivation right there, is to basically have this hidden away, self-sustaining, and isolated.
And so what about the height of the panels, right? Can't you put the panels lower down near the roof?
Yeah, I thought
Okay.
I meant, I'm sorry for that.
This is depending of the roof that we encounter.
The orientation.
Yeah,
Okay.
So we come with we try to do some type of inches that we can lower and change the level of the.
But just in general, right? Get them closer to the roof. Maybe, I understand like turning them, I don't know.
By
Anyway,
closer
I see what you're saying.
You mean down here?
Yeah, but then
Yeah.
you lose some from the far side panel, right? I don't know,
Right.
it's hard.
We
It's
wanted to
hard,
give the
yeah.
option, in a perfect
Right.
world, if we had more money, like I said, these would be adjustable.
Uh-huh.
And depending where you live, let's say this direction is, no sun comes up in this
Right.
direction. This panel would then be this way, this panel would then go
Right.
down. Since it's
Right.
not gonna get anything from here, this panel doesn't need to be up.
Right.
So wherever you spin it, you say, okay, there's my sun, there's where I don't get sun. Put it
That
this
makes
way,
sense.
this panel goes up, this goes up. And it would actually not have this symmetry about it. It would have basically different orientations. It's like satellites tend to do.
Right.
Not that I'm comparing this to a NASA satellite.
It looks like one.
Yeah, thank you.
It could end up being a satellite.
We recommend.
All right, thank you very much. Very good.